Primary Flight Control System. In this lesson, we will discuss the primary flight control system covering the following topics: the primary flight control surfaces, pitch, roll, and yaw control, input from the pilot controls, the primary flight control system mechanism, a primary flight control system mode overview, a protection function overview, unique failure considerations, and ICAS messages. The control surfaces operated by the primary flight control system are 2 ailerons, one on each wing. The ailerons are located outboard of the outboard flaps. 2 flaperons, one on each wing. The flaperons are located between the inboard and outboard flaps. 14 spoilers, 7 on the upper surface of each wing. The spoilers are numbered from left to right, 1 through 14. Spoilers on opposing wings are symmetrically paired. 1 movable horizontal stabilizer, 2 elevators, one on each side of the horizontal stabilizer, and 1 rudder. The primary flight control system operates the control surfaces to provide pitch, roll, and yaw control. 2 elevators and a horizontal stabilizer work together to provide pitch control. The ailerons, flaperons, and spoilers provide roll control. The flaperons also provide added lift by droop when the trailing edge flaps are extended to improve slow-speed performance. The spoilers assist the ailerons and flaperons in providing roll control. Yaw control is provided by a single rudder. Flight deck controls consist of the control columns, control wheels, and rudder pedals. The columns, wheels, and rudder pedals are connected through jam override mechanisms. If a jam occurs in a column, wheel, or rudder pedals, the pilots can maintain control by applying force to the other column, wheel, or rudder pedals to overcome the jam. The speed brake lever allows manual or automatic symmetric actuation of the spoilers. Let us now look at how control input is translated into surface control movement. Pilot input to the control column, wheel, and rudder pedals will be converted to electronic signals. These signals are sent to 4 actuator control electronics, or ACEs, namely the left, center 1, center 2, and right ACEs. The ACEs transmit pilot control input to 3 primary flight computers, PFCs. The PFCs use information such as air data, inertial data, flap and slat position, engine thrust and radio altitude from other airplane systems to compute control surface commands for enhanced handling qualities. The PFCs are the center of the flight control system. They calculate flight control position commands requested by the pilot, relaying them back to the ACEs. The ACEs now receive computed data from the PFCs and transmit it to the respective power control units, or PCUs. The PCUs provide the force to operate flight controls with the help of hydraulic power. When the autopilot is engaged, it sends signals directly to the PFCs. These signals are then sent to the ACEs and then to the control surfaces. The autopilot also sends commands to move the pilot controls, giving the pilot immediate feedback relating to autopilot input. If the pilot performs control input, the autopilot will disengage. The flight control system will then apply the pilot input. The primary flight control system is highly redundant with 3 operating modes: normal mode, secondary mode, and direct mode. All the modes use the same pilot controls and flight control surfaces. Aircraft usually operate in normal mode, and all flight control system functions and flight envelope protections are available in this mode. In the event of multiple system failure, the primary flight control system changes to secondary mode or direct mode. We will learn about these primary flight control system modes in more detail in coming lessons. The primary flight control system has a number of flight envelope protection functions that operate in normal mode. The functions include stall protection, overspeed protection, and bank angle protection.
Bank angle.
There is also automatic input for lateral and vertical wind gust suppression and asymmetry compensation. Vertical and lateral gust suppression enhance ride quality and reduce pilot workload, but do not result in control wheel, control column, or rudder pedal movement. Vertical gust suppression is only active with the autopilot engaged in altitude hold or VNAV level flight modes. On the ground, that is takeoff, and in flight, that is go-around, are different in asymmetry protection. On the ground above 60 knots, the system puts in most of the rudder to let the pilot know there is a failure. In flight, the system enters the required rudder input, and the rudder pedals move to inform the pilot that there is an asymmetry situation. The rudder trim is also automatically shown on the ARCS display. The thrust asymmetry protection function will decrease the power of the remaining engine if necessary, so that sufficient yaw control is always available. Once airborne, 100% yaw control will be provided. Let us now look at some of the unique flight control failure redundancies of the Boeing 787. In the unlikely event of the loss of all hydraulic power, the electrically actuated stabilizer allows pilot control of pitch. This is performed by using the primary pitch trim switches or alternate pitch trim switches, as well as roll control by electrically actuating spoiler pairs 4 and 11, along with 5 and 10 using the control wheel. If there is a complete loss of flight control signaling, direct wiring from the flight deck to the stabilizer allows pilot control of pitch. This is performed by using the alternate pitch trim switches. Direct wiring from the flight deck to a spoiler pair allows pilot control of roll using the control wheel. The following are primary flight control system ICAS messages that may appear during operation. Click on each ICAS message to learn more. You have reached the end of this lesson.